So fluid dynamics is that branch of fluid mechanics which deals with the study of behavior of the fluid in motion. So therefore, so with reference to forces causing the motion. So in the case of fluid kinematics, we were dealing with the geometry of motion of the fluid without reference to the forces causing the motion. Here only, there only velocity, acceleration, like this, the movement of the particles were discussed. But in fluid dynamics, we are concerned with the forces that are causing the motion. So therefore, there will be a resulting change in the variations in the acceleration. So whenever there is change in the accelerations, also there is a variation in the energies which is involved in the flow phenomena. So that's why your famous Newton's law comes here: force is mass into acceleration. So therefore, resulting in the variations of the accelerations, there also will be the net force developed. So in this case, so we are studying mostly with the forces and energies that are involved. So that type of study in which the forces and energies are involved are known as dynamics of fluid flow. So therefore, we can say that dynamics is nothing but it deals with the behavior of fluids in motion with reference to the forces causing the motion. So therefore, so this is what we are. So you might have heard of Newton's law. So where any particle or any body is moving, so with some accelerations, then the net force is equal to mass into acceleration in that particular direction. So net force will be exerted in that directions. So when we are talking about the forces, what are the various forces that are acting? So the various forces can be the body forces or the volume forces. So body forces are those forces which are proportional to the volume, okay, which are proportional to the volume, for example weight. Then surface forces are those forces which are acting on the surface areas, for example tensile force, compressive force, turbulent force, pressure force, earth pressure. These are all which are acting on the area, so therefore they are known as the surface forces. And line forces are those which are proportional to the length, for example surface tension force is the line force. So because that is the force that is exerting per meter length. So therefore, surface tension force is a line force, whereas all the forces that we studied, like pressure force, earth pressure force, the tensile force, compressive force, shear forces, are all the surface forces, whereas the weight or magnetic force or gravitational force are known as the body forces. So body forces or volume forces are the forces which are proportional to the volume of the body. For example, weight, centrifugal force or magnetic force. And also the surface forces, the next is which is proportional to the surface area, which can be pressure force, it can be shear force, it can be or tangential force, compressibility force or turbulent force. So whereas the line forces are which are proportional to the length, for example surface tension forces. So here we are dynamics of fluid are generally is governed by Newton's second law of motion. You know that Newton's second law of motion states that the resultant force on any fluid element should be equal to mass into acceleration, and that acceleration because force is a vector quantity, so acceleration is also in a vector quantity. So acceleration vector has to be in the same direction as the force. So that is what the net force direction, and the acceleration vector has the same direction of the resultant vector. So in mathematical form, you know that summation of all the forces, the net force is equal to mass into accelerations. So now this summation of F is resultant external forces, the net force that is acting. Okay, so there may be various forces acting. You've tried to find out the net force in that the direction in which the net force is acting is also the body will move in that particular direction. Okay, so that is what it means. So M is nothing but mass, and A is the total acceleration. So here, so now since the acceleration resultant external force or net resultant net forces should be in the same line of action. Okay, if it is in horizontal direction, say the horizontal. So that means if it is in a vector acting in some particular direction, it can be resolved into three directions like x, y, and z. So when you try to resolve it, so you can separately write the equations like this: sigma fx is equal to mass into acceleration in the x direction, sigma f(phi) is mass into acceleration in the y direction, sigma fz is mass into acceleration in the z direction. So okay, like this, and these components sigma fx, sigma phi phi and sigma f z are the components of the resultant force, okay, which are acting in x, y, and z direction. Similarly, ax, ay, az will be the components of the total accelerations that are acting in x, y, and z directions. A simple Newton force. So based on this only, your Bernoulli's equation, everything is derived. So now coming to this, what so when I'm telling so much about the forces, so what are the various forces that will influence the motion of the fluid? So the most important force is the gravity force. For example, weight, so mass into acceleration due to gravity. So gravity force is m into g. Similarly, whenever there is a pressure gradient between any 2 points, then the pressure forces will be acting. For example, in flow through pipes and all, so where there is a pressure gradient or difference of pressure between any 2 points, then the pressure forces will be acting. Similarly, in a thin sheet of water, where one layer of fluid is moving over another layer, there is always resistance to flow. So that time viscosity or viscous force is very predominant. Similarly, when the Reynolds number is more than 4,000, so where there is a lot of mixing up of particles, especially when the velocity is very high, then we have what is known as the turbulent forces. And also, when there is a rise of water or maybe a droplet, somewhere where the surface tension force becomes very, where a narrow passages are there, then surface tension forces. Similarly, for compressible fluids, particularly for mechanical students, the more compressibility force is more important. So then these are the main forces which we are likely to consider in the motion of the fluid. So as I told you that gravity force is due to the weight of the fluid, that is equal to m into g. So you can also tell that gravity force per unit volume. So mass by volume is density. So density into g. So that means rho into g is also known as mass, the gravity force per unit volume. So okay. So anyway, gravity force is due to the weight of the fluid. That is weight. Weight is nothing but mass into acceleration due to gravity. That mg by volume is m by v. M by volume is rho, so it can be said that gravity force per unit volume is also known as rho into g. Okay. When there is a difference of pressure between any 2 points, so then there is a pressure force exerted. So you can also calculate the pressure force between any 2 points. So we have done a lot of problems in the measurement of pressures, but to find out the difference between the pressure between any 2 points, and then that once you get the pressure, you can multiply by area and calculate the pressure force. Similarly, the viscous force is due to the viscosity of the flowing fluid. So, therefore, all real fluids definitely have resistance to the motion of the fluids, and therefore, we have viscous forces. The turbulent forces is due to the high velocity, due to the turbulence of the water. Here, mixing up of the particles takes place. So, the continuous momentum transfer takes place between the different layers of the fluid, which results in additional stresses, which is also known as Reynolds stresses for the flowing fluid. So, for example, there may be a objective type where what is Reynolds stresses? Reynolds stresses is the stresses that is developed between the continuous momentum transfer between the different layers. So such type of generally occurs in the turbulent when there is a turbulence in the flow fluid. Okay. And surface tension, it is due to the cohesive property of the fluid mass. It can be when the depth of fluid is extremely small, or when there is rise of water. So this surface capillarity, where there the surface tension forces will be acting all along the periphery. And the compressibility is whenever you have a compressible fluids, so then this elastic property, particularly in water hammer problems, you might have studied in fourth semester, or third semester, where the water hammer comes there, the compressibility force also comes into picture there. So this type of where the elastic properties are involved, so such forces are known as compressibility forces. Now, so why I told all these things is that so now we go on eliminating all the forces and try to apply two forces. That is how we come to most important two forces is the gravity force and the pressure force. So taking these two considerations, we go ahead with the derivation of Bernoulli's equation. So now, so here when you apply Newton's second law of motion, summation of the forces, that is net forces, is equal to the summation of all the forces. That is gravity force, pressure force, viscous force, okay, turbulent force, surface tension force, and the last compressibility force. Okay, so like this you can apply. So this is the most general equations. But when you consider the problems of fluids in motion, generally the surface, because surface tension forces are very small, and generally we consider incompressible fluid for our cases. So therefore, when you consider incompressible fluids, compressibility forces are also not that significant. So therefore, the surface tension forces and the elastic forces are neglected. So this is taken out. So that means we are left with only four forces, that is gravity force, pressure force, viscous force, and turbulent force. So this particular equation is known as Reynolds equation of motion. So yeah, because the turbulency is also considered in this equation 4, so generally this Reynolds equation of motion is used in the analysis of the turbulent flow, because you have always gravity force and you also have pressure force, and if there is resistance to the flow, then there is viscous flow. So therefore, so we apply to the analysis of the turbulent flows, where which is known as Reynolds equation of motion. But when we consider the laminar flows or the viscous flows, for example, where a thin sheet of water moving or the velocity is quite less, then turbulent forces are also becomes less significant. So therefore, it can be neglected. And this equation where we neglect the turbulent forces is known as Navier-Stokes equation. So when I come to the next few chapters, that is laminar flow, then I will be discussing about the Navier-Stokes equation. This you have not studied in your BE days. So laminar flow was not at all there. The entire chapter of laminar flow and turbulent flow was not there. But in GATE, they have included laminar flow separate chapter and turbulent flow as separate chapter. Which after energy concepts and all, I will be discussing about laminar flow, boundary layer theory. Those things will come in laminar flow. So there, where we discuss about Navier-Stokes equation. So generally applied for the viscous flow. So now, when we go for the flows where the viscous force is quite or little significance and can be neglected. For example, if we make an assumption that the fluid is ideal, whenever the fluid is ideal, then the viscous forces or surface tension forces and all these forces are eliminated totally. So therefore, however, in case of real fluids also, the viscous forces are quite insignificant if viscosity of the fluid is quite small. So therefore, this boils down to two forces, which is gravity force and pressure forces. So this equation is known as the Euler's equation of motion. So now we are coming to Euler's equation of motion. So when you say Euler's equation of motion, which are the two forces which are considered in Euler's equation, and finally into Bernoulli's equation is the gravity force and the pressure forces. So therefore, in the objective type, when they ask you what is which are the forces that are considered, for example, in Euler's equation is gravity force and pressure forces. If in Navier-Stokes equation is gravity, pressure force, and viscous force, and Reynolds it is all this gravity, pressure, viscous, and turbulent forces. So like this is called Reynolds equation. When you neglect turbulent, then it will become Navier-Stokes equation. So when you neglect viscous force, then it becomes the Euler's equation of motion. So therefore, so now what we finally arrived at in Euler's equation of motion is that, so only two forces to be considered. One is the gravity forces and the pressure forces. All other forces are neglected. So except the gravity and pressure forces, no other forces are considered. So then, in order to eliminate the viscous forces, we assumed ideal fluid. So therefore the ideal so the assumption is that the ideal fluid. So then to eliminate compressibility forces, we took it as incompressible fluid. So therefore that also becomes assumptions of Euler's equation. Okay, then in order to apply Euler's equation in one particular direction, we have to consider one particular streamline flow. So therefore, the flow will be along a streamline. So these are some of the things that you can consider or you can assume, so that you try to eliminate all the forces except gravity and pressure forces. So that's why we have what is known as the Euler's equation of motion. So I'll not go deep into this because you know all these equations. So only two forces are considered. One is the pressure forces, another is the gravity force. Gravity force in the sense is the fluid weight, or generally we call it as the body forces, which I told you right in the beginning. Uh, So in this case, we have assumed that fluid is non-viscous here. That's why I said that that viscous force uh, is not there. So therefore non-viscous. So therefore the pressure forces which will be this, you would know that it is because of this. There is no like tangential forces. So therefore the pressure forces that you studied in your second chapter also, the pressure forces have to be acting normal to the surface. So therefore when I put pressure forces, it will be normal to the surface because of this assumption. So now this is uh, the fluid element that we have taken. So now see, coming to this, we have a streamline. Okay, so like this is a streamline which is also known as the direction of the flow. So we have taken out a free body. Okay, so like this is a fixed volume, so where from which the flow is taking place. Then we have taken out an element. So element is ds, okay, of cross section area dA. So if the cross section area is dA and the length is dA, okay, so there are two forces. One is the pressure forces. So the pressure force should act on AB and also should act on CD. Okay, so which is normal to the face. So now the pressure intensity into area will give force. So similarly, if the pressure intensity is P, so what is the pressure intensity here? So pressure intensity, because it is we are moving in the direction of the flow, so it is plus now. So P plus something which is dou P into instead of writing dou P by dou S into dx like this, I directly wrote the increment. So P plus something, so which is dou P into dA. Okay. So now we also have the weight of the fluid element. So what is weight? Weight is nothing but specific weight into volume. Specific weight, you know, it is rho into g. Rho into g. Volume is dA into ds. Okay, so therefore, so let it be acting at an angle theta. So suppose you take some triangle, something like this. So if this angle is theta, this angle is also theta. So therefore, this is angle theta. Suppose if this, so this length is ds. This length is ds. So therefore, this is also ds. So if this is angle theta, so this length you can take it as something like dz. Dz, this can be taken as dx or something, which we don't want this. So anyway, I have considered this as dz. Okay. So coming to this now various forces, I have told you that these are the various forces which are acting, which is this force, pressure force here, pressure force here, and the weight of the element. So now what does your Newton's law states? Newton's law states that net force should be equal to mass into acceleration. You cannot put it equal to zero because the fluid is in motion now. So all the in fluid statics used to say that it is equal to zero, but now you cannot say. So now from henceforth onwards in this motion, whenever the fluid is in motion, net force is equal to mass into acceleration. So you should say mass into acceleration. You cannot equate to zero. So plus don't equate to zero. So when you do this, we are resolving the force in the right. So PdA is positive. This is minus, so therefore minus. So then this component in the direction of flow, if you resolve, it will be cos theta. So it means entire the rho g dA ds into cos theta. If you do it, you will get the component in this direction, opposite to PdA. So therefore, it is minus. Should be equal to mass into acceleration. Acceleration is in this direction, in the direction of the flow, in the direction of net force. Okay. So this is what we do. So now you split up the terms. So P dA minus P into dA minus rho P into dA minus rho G dA ds cos theta. But what is here the mass. So mass is density into volume. Mass is density into volume. So density into dA ds, which is the volume. So acceleration can be written as change in velocity by time, or dou v by dou t. Okay, so this gets cancelled out. So dou p dA gets cancelled out. So you're left with minus dou p dA with this term. So then this term can be dou v by dou t can be written as dou v by ds into ds by, so multiply and divide by ds. But ds by dt can be written as velocity because displacement by time. So this can be written as velocity. So one velocity term will come. Okay, so ds and ds cancels out. So this gets cancelled out. Okay, so here this gets, sorry, this is mm, this two gets cancelled out. Okay. Okay. So now you're left with this minus dou p dA. So this ds cos theta. Similarly, this was same term I wrote. So finally, I end up with rho dA v into, so ds by dt can be written as velocity. So now cos theta from here, cos theta is nothing but dz by ds. So you replace dz by ds. So when I replace there, so ds gets cancelled out. Okay. So I'm left with this term. So now, so this finally rearranging this, so we'll get minus, so dA cancels out. So dividing by dA throughout, dividing by dA throughout, dividing by dA throughout. So you will get this term. So now this is rearrange this term and integrate this. Okay. So if you integrate this, so you can write it as dou p. So taking out so they bring this row v dou v this side, all will be minus. So taking out minus sign, so we have this term. So now you can say that you can divide by row, for example density, so there will be dou p by row. This will be this row goes, so v dou v, so then will be g into dz. So this equation is known as the differential equations, or Euler's equation, which is also known as Euler's equation of motion. So now this is the, so this we don't use in any of our problems, because it is in the differential form. So this differential form, will try to convert it, you try to integrate this. So when you integrate it, so when you integrate this dou p, so integration of 1 is p, so it will become p by rho. If you integrate this with respect to velocity, so v square by 2. If you integrate, g is a constant, integration of 1 is z, so integration of 0 is a constant. So you get most famous Bernoulli's equation. So therefore this was the equation. If integrating this, so you get p by rho plus v square by 2 plus g into z is a constant. So now you can divide by g. When you divide by g, you will get p by rho g, that what you know, plus v square by 2g plus z is equal to, constant by g is a constant. So therefore we get this known as p by rho g is omega, you can also write, or you can remember as p by rho g also. So this is known as the Bernoulli's equation. There are three terms in this. So each is the in meters of units. So this is the pressure head. So this term is known as the velocity head, and this term is known as the datum head. So that means the summation of pressure head, the velocity head, and the datum head is a constant, which is known as the, because each is a meter unit. This is meter unit. This is meter unit. This is meter unit. So therefore, your constant also should be in terms of meter, which is known as the energy head. So therefore, the summation of pressure head plus the kinetic head or velocity head plus the datum head is a constant, which is known as the energy head, which is in meters. So now you can say that each is a energy per unit weight, which we know. So therefore, it is energy concept. So pressure energy per unit weight. So this is the kinetic energy per unit weight. This is potential energy per unit weight. So potential energy means if you take a weight and lift it by z, so then you will get a potential energy, which is W into Z. So this is potential energy. So you are lifting by Z. So that means if you divide by W, it will become Z. So that's what it is the meaning. Similarly, if you take kinetic energy half mv square and divide by weight, so you will get v square by 2g. So it is kinetic. So if you take pressure energy and divide by unit weight, so you will get so each is energy per unit weight. So therefore, which is known as, this is known as the pressure head. So you know that it is a pressure head which is in meters. V square by 2 is known as velocity head or kinetic head in meters. Similarly, Z is the datum head, again in meters, or potential head in meters. So therefore, the right hand side is a constant, which is also known as the energy head. So now you should be able to find out what is the total energy head, that will give in meters. So therefore, now you can define what is known as Bernoulli's theorem. So Bernoulli's theorem. So for what we applied for a steady flow, because a wave flow is along a streamline, and that streamline won't change with respect to time. So therefore, we assume that it is a steady. Similarly, the the centrifugal force and all the other forces were eliminated, so irrotational flow. Or if you consider ideal fluid, then it is irrotational flow. Then we eliminated compressibility fluid, so therefore incompressible fluid. So therefore, while stating Bernoulli's theorem, you should state that for a steady irrotational flow of an incompressible fluid, the total energy head remains constant. So that means the summation of P by omega plus V square by 2G plus Z is a constant. So that means if you move from one section to another section, the total energy head, pressure head may change, velocity head may change, but Z may change, but the summation won't change. So that is the meaning of Bernoulli's equation. So therefore, you can try to apply between any two sections. But whenever the flow takes place from one section to another section, always there is a loss that is taking place. Loss may be due to many types like friction loss, or maybe bends loss, anything like that, or fitting loss or this. So total loss is AHL. So we say that we always apply when the flow is taking place from one section to another section. We apply to the second section always. So therefore, if the flow is taking place from 2 to 1, so then we apply HL to this side. So it depends. I'll tell you in the problem. So there you'll come to know. So therefore, this is the head loss between section 1 and section 2. So therefore, the total energy head at section 1 is equal to total energy head at section 2. Okay. So so this is the graphical representation of your Bernoulli's equation. I told you that this is section 1, this is section 1, and this is section 2. So what does this physical meaning of this thing is that, so it's here, whenever you take a datum, so what is the height of that point? So that is represented as Z1. So this point is at a height, so it causes a potential energy per unit weight, Z1. So because when the water is moving from section 1 to section 2, there is there is always a pressure. Because of pressure P1, the water will rise to this. If you fit a piezometer, the water will rise to this height. That is what you studied in your pressure chapter. So that is H is equal to P omega into H. So that is P is equal to omega into H, or H is P by omega. So therefore, depending upon the pressure here, so the water should rise. Okay. So now, as the area is more, velocity is less. If velocity is less, pressure is more. Similarly, when you go over here, area is less, velocity is more, so pressure is quite less. So therefore, the pressure head here is always drops from the pressure head here. So therefore, as flow takes place, there is always resistance to the flow. So therefore, that's the reason why the P2 by omega is quite less than P1 by omega. But the pressure and velocity gets adjusted so that the total energy head will remain same. So that's the reason. That is what Bernoulli's theorem. So though this quantities changes between section to section, this quantity changes, but the total always remains the same. So that's why I have marked it as this. This is the total energy head. So therefore, you can see that the summation of all these three terms and summation of these terms are always same. So if for example there is a loss taking place from this, so what you do is this is, so you can mark, so this only v2 square by 2g till here, and this you can mark is as HL. So now the Z2 plus P2 by omega plus V2 square, which is still here, plus HL will be equal to total energy, which is same as this. So that is how you represent. If there is no loss, so then this V2 square by 2g will come till here. Okay. So this is your graphical representation of Bernoulli's equation, which I wanted to tell. So physically you can see that okay, they what are those ordinates of our Bernoulli's equation. These three terms are represented graphically. So therefore, while we derived the Bernoulli's equation, these are the factors that we took. So that assumptions that are made. So flow is along a streamline. So if you want to apply for some other streamline, then you have to apply the different equation for Bernoulli, so that velocity will change and all that things. So therefore, we have considered the steady flow so that we can apply Bernoulli's equation for one particular streamline. And fluid is incompressible, flow is steady and irrotational. Then only two forces we have considered. That's why when I started Euler's equation, only gravity force and pressure forces were considered, and no other forces were considered. And velocity is uniform across the section. So for example, when I take a section here, whatever velocity I have taken here as v1 is uniform across this section, but actually it is not so, which I will come later on, which we call it as a kinetic energy correction factor. So here the velocity, maximum velocity will be here at the center line, and then it will become zero. So like this, though there is a variations of velocity along the section, but actually we have taken as it is a uniform velocity. So because of that, we have only taken v1 square by 2g. Actually, we have to multiply a factor known as alpha, which is known as the kinetic energy correction factor. So later on, when because that also will be very useful, when alpha values are given to you, you can always modify that velocity head by multiplying by alpha. So that if it isn't given in the problem, you can take it. Otherwise, you can take it alpha is equal to 1. So these are the concepts of the energy. So now you should just 4 or 5 problems to understand what is energy concepts and how to apply Bernoulli's equation. So because we have seen many a times such an easy problem, because just by applying Bernoulli's equation you will be able to calculate the various terms. So the pressure at one point will be given, and they tell you to find out the pressure at the other point, or something like this. Okay, so this, if you know this Bernoulli's equation and how to apply, so then the applications of Bernoulli's equation, which will be told in the next class, in few classes more. So fluid dynamics will take little time because we have a lot of applications in this. So that's why today I'll be telling only how to apply Bernoulli's equation to a particular problem. Very simple questions with 1 marks, so which directly you can solve it. So like this. So for example, a zero point 0.3 meter diameter pipe is given. So it is a uniform diameter pipe. Okay, it is a uniform diameter pipe. So where because uniform diameter means you know the continuity equation, section 1, section 2, discharge will remain same. If discharge remains same, diameter is same, then velocity also will remain same. So therefore the velocity at section 1 and velocity at section 2 are same, so which is 2.5 meter per second. But when you measure the pressures is given as 36.1 kilonewton per meter square, and the point is 3 meters from the datum. Similarly, the pressure at the second point is 28.8 and 4 meters above the datum. So for steady flow, you have to find the loss of head between the point 1 and 2. So therefore, here whenever they ask you what is the loss of head between the between point 1 and point 2, so generally what we do is for point 1, we'll calculate what is the total energy head. For point 2, we'll calculate what is the total energy head. Okay, so when we are able to calculate the total energy at point 1 and total energy at point 2 separately, then see which point 1 has got more head, more energy head, not pressure head. I'm talking total P by omega plus V square by 2g plus Z. So also, so if suppose energy head here is more than the energy head there at 2, okay, energy head at 2 is less, so then flow is taking place from 1 to 2. Suppose energy head at point 2 is more than point 1, then the flow will be taking place for like this from 2 to 1. So this problem will tell you how the flow is actually moving. So because you know that flow always moves from high pressure, not high pressure to low pressure. It is always high, and because this total head will depend upon all the three terms now. So from here onwards, you say that it is pressure head, velocity head, and datum head. So on all the three terms, it will depend, not only on pressures. Okay. So therefore, whenever you decide the direction of the flow, it should be the total energy heads. Okay, so that is what we are doing. So these are given. So now you should be able to calculate what is the total energy head at section 1. So if you know P by P1 by omega, that is 36 because kilonewton. So specific weight of water is 9.81. So this corresponds to what type of fluid is flowing in the pipe. So here if it is water, so it is 9.81. So you know how to calculate because velocity is given. In this case, since it is uniform diameter, so velocities are same. So velocities are same. Okay, so therefore v1 square by 2g I have calculated. So it is 3 meter height from the datum. So it is 3 meters. So therefore total head is 7 meters. Similarly, if the total energy head at 2, if you want to calculate, so same, take the data of section 2 and calculate. So you'll get 7 points. So you can see that section 2 is more than section 1. So therefore the flow will take place from section 2 to section 1. So what is the loss? It is always the difference between these two. So therefore, if you want to calculate loss, so it is 0.254. But since the energy head at section 2 is more than energy head at section 1, the flow is taking place from 0.2 to 0.1. So this is this type of question. So one line, they directly you should take calculator and start calculating, and note down the total pressure head, total energy head. Similarly, take a calculator, simply directly without writing, you can just type it on your calculators and find out energy head at point 2. So then see which head is more. So the flow will take place, okay, from that point to the another point. So these are the this type of problems. Here I have considered uniform diameters. Sometimes they will give the tapering bars, and the diameter will change from section 1 to section 2. So when the diameter changes, then velocity changes, okay. So because q is a1 v1, that is also equal to a2 v2. So from there you can try to find out. So here the see, now I have considered, so where I have changed the diameter now. So so water is flowing through a tapering pipe. So here section 1 and section 2. So section 1 we have 10 centimeters is the diameter. Section 2 we have 20 centimeters diameter, and the heights also. Section 1 is at 3 meters and this is 5 meters. Okay. So now pressure is given at section 1 is given. So you have to find what is the pressure at section 2. Here nothing is mentioned about the losses. So therefore the total energy head at section 1 should be equal to total energy head at section 2. So specifically because there is no loss given, so therefore you don't consider the loss. Then total energy head has to be equal to total energy head at section uh, 2. So that is what it means. So now before we go to the problems, because it is a tapering bar, you should know how to calculate the velocity. So simple velocity calculation, you know, that is q by area, which is q is given. So 0.03, you divide by the area, so you will get the velocity. And then you can also calculate the velocity at section 2 by taking the respective area. So here the diameter is zero point 0.1 in section 1 and zero point 0.2 at section 2. Similarly, the velocity. So now you know that if the diameter increases, that is the area increases, so the velocity decreases. So the velocity which was 3.82 gets reduced to 0.95 meter per second. But you know the this also. So only thing is the unknown quantity is P2. So if you equate like this, that is P1 by omega, because water is flowing, so 9.81 P1 by omega plus V1 square by 2g plus Z equals P2 by omega plus V2 square by 2g plus Z2. So if you do this, then you will get the answer. So this is in terms of kPa, which is 17.224 kilonewton per meter square. So this type of problems can also be asked. If there is no mention of loss of head, so please don't take it here. So unless they ask you, so if for this problem, if they had asked you what is the loss of head, then they would have given the pressure. So they would have given this pressure, so something like so that you can find total energy at section 1, total energy at section 2, take the difference, and you would have got the loss of head. So since nothing is mentioned here, you cannot solve the problem unless you take loss of head is equal to 0. Sometimes loss of head will be given and we have to solve the problem. I'll come to that also later on. So now with two problems you came to know. One is to find the loss of head, another is to just find one. P1 is given, try to find out P2. So this is the problem. And here also I told you that velocity will change from section 1 to section 2, so because of the diameter change. Okay. Now the same thing here, the same tapering bar, but same thing here. It is 1.2 meters diameter, which is at the high end, and zero point 0.6 meters at the low end. So again, the diameters are changing, but here the velocity, the discharge is given, which is 54,000 liters per minute. So 1 liter is 10 raised to minus 3 meter cube, multiply by 10 raised to minus 3 and divide by 60. So you have to work out the problems only when in meter cube per second only. And here this is okay, 68 points. So pressure at the higher end is given. You have to find the pressure. It is similar to the previous problem, but only thing is the slope is given here. Slope is given. So which is 1:100. Last time the problem was Z1 and Z2 were given to you, but in this problem Z1 and Z2 are not given to you. So you have to find out from this slope. So that's the difference between the previous problem and this problem. So whenever the slope is given, I will represent by the means of a sketch for you. So yeah, so this is the sketch. Okay, so when you have, so I told you that so the tapers from 1.2 meters at high end. So high end I have taken as 1.2 meters, low end I have taken as point. So this is low end, this is the high end. Okay. So So the quantity of water, that is 54,000 liters per minute. The pressure at the higher end. So pressure at the higher end is given, which is 68.67 kPa. Okay. So you have to find the pressure at the. So this flow direction is also given to you. So when the flow direction is given to you like this, so I have considered this as section 1 and this as section 2. So now it is your choice to pass the datum. So where you want to pass it. So whether you want to, if you pass the datum here, so then this distance is not known. So therefore take this datum and pass it through section, are always at the lower section. So now you can see the, since the datum is passed here, so z1 will be 0 and z2 you have to find out. So z2 is based on this slope. So z2 is always, so because tan theta is 1 by 100, so which is also equal to, if this is theta, this is also theta. So therefore sin theta is z2 by this length, yeah, 300 meters, 300 meters. So now that means, uh, why I'm telling all these things is directly, we no need to write all this. So tan theta is, by taking the slope, tan theta is 1 by 100, whereas sin theta is z2 by 300, z2 by 300. Okay, so this is 300, from here to here is 300, and this is z2, so this angle is also theta. So you go, this is theta. So now, so if theta is very small, tan theta is equal to sin theta, so that means z2 by 300 is equal to 1 by 100. That means if the slope is given, z2 can be calculated directly by slope into the distance, that is 300 meters. So therefore that's the reason why z2 can be calculated, which is 1 by 100 into 300. So once you know this, then rest all is to substitute. So calculate the velocities, because discharge is known. So then calculate the velocity at section 2, apply Bernoulli's equation. So when you apply Bernoulli's equation, only thing is that last time Z1 and Z2 were given, now you are able to calculate. So that's the difference between this problem and previous problem. So Z1 we are passing this. So always pass here so that you will get positive values. So don't pass the section here, so that you should write minus and all, so it will be wrong. So what you have to do is you have to pass it here so that you get all positive quantities. Okay, so you move upwards. So here z1 is 0 and here z2 will be this value. Okay, so that is what we calculated. So knowing this, then the pressure can be calculated, which is 93.345 kPa. So this is the
Sir,
yeah.
in each case, how we will come to know that another end is on datum, sir?
No, no, no.
Z2, Z is 0.
No, no, no. See here, see when the flow is taking place like this, you always place it on the lower section only. Always place it on the lower section. Now see the flow direction. See the flow direction. When the flow direction is that, this will become section 1 and this will become section 2. So if there is okay, like that. So now you pass this. So
Yes.
if you had passed the datum, you would have told this as x. So and here also this is x. So it is x plus something. Then again x will get cancelled out. Instead of doing that, you pass your datum here only, so that you will come to know always at the, so that you will get positive values. Upward is positive always, so that always pass it on the lower section only, don't pass it on the upper section. Okay,
Okay.
so these
Okay,
things,
sir.
even the flow is taking place like this downwards, pass it here only. So then when the flow is taking place, if you want, you can name it as 1, or you name this as 2 and this as 1, no problem, but to pass it always this one here only. Okay, suppose if the flow was taking downwards, no problem, you pass the section down only. Okay, because then whatever you name, if you name 1, then it is z1. If you name this as 2, then it is z2. If you name this as 1 and this as 2, you would interchange these values, that's all. So it depends on how you name it. So naming is not a problem for me. So only thing is, they have told pressure at high end is this much, pressure at low end is this much. So we are concerned not with section 1 or section 2. You can name it as A also, you can name it as A and this as B also. Okay, my concern is how to pass the datum. So passing the datum is always at the lower end, so that you will get positive values. Got it?
Yes, sir.
Okay. Now see here. So this was the problem where the head loss is given. So now all this case, all first problem we found out head loss. Second problem, third problem we didn't find head loss. But now head loss is itself is given to you. So head loss is 3 meters for you given. Okay, this you have to take care in the Bernoulli's equation. So please see that if head loss is given or not. So now one more addition is that what we did is that instead of water, we are having oil of specific gravity 0.8. So when you're taking P1 by omega, it should be specific weight of oil. So it should not be for water. So the pipe changes the diameter. So I have given section A, section B. You can write 1 and 2 also. So from 300 mm, it changes to 450 mm. So, and also it is very clearly given that point B is higher than point A. Okay, and pressures are given. So again, you have to find discharge of the oil. So now, so this is the sketch. So you can write it inclined, you can write it vertical, but show that B is more than A. That's all. You can write it inclined also. It will not make any difference for the problem. But because the vertical distance is given to you. So because B, they have said that it is 4 meters higher. So now where shall I pass the datum? So now how the this one, the head loss, the pipe changes in diameter. The point B is 4 meters higher. If the pressure at A is 120 kPa, here it is given, and determine the discharge of the oil. So therefore, we have these data. So now, see what happens is the diameters are given. Okay, so discharge you have to find. So now, what is our the concern is to find the relation between V and or V1 and V2. Okay, so therefore we apply continuity equation. So when we try to apply continuity equation, so pi by 4 d square, okay, equals pi by 4 d square, this pi by 4 d square here, and then velocities, corresponding velocities are A and B. So VA and VB. So we get a relationship between VA and VB. So this is what we found. So this we try to substitute in our Bernoulli's equation. So see here. So the loss of it between A and B. So between A and B, that means the flow is taking place like this. Between A and B, it is given. So from A to B, if when we move, so that is the loss is 3. So that's why I've added the loss term to the second part. So because if the flow is taking place from here to A to B, then you have to add the loss to the second section always. So therefore, the second section we have added here. Okay, so this is only the addition thing is there. So what happens is that this is given, this is also known. What is ZA? It is 0. What is ZB is directly 4 meters because it is from the datum 4 meters. So so velocity you can write VA in terms of VB here. So all that this term is also known. So what happens is VA is in terms of VB, so VB will come out. So that means velocity at section B will come out, then discharge can be calculated. So this is how we try to find out the from the same equations. We are applying VA in terms of VB, which is 2.25 VB square. So therefore we'll get. So you can also write VB in terms of VA and substitute VB also, whatever you want. Okay. So now and VA also can be calculated from this relation, which is 2.25 into 3.03. So either you take A1 V1 or A2 V2 or area into velocity for section B, or you take section A. Both will give the same answer. So discharge is corresponding area into velocity, or you can also take the second equation also. So because both are same continuity equation. So either you take this diameter area and then multiply by the corresponding velocity VB. So both should give the same answer. So that is the continuity equation. So whatever discharge passes here has to pass here. So this is the so what is the significance of this particular problem is that, so now so what we did is that here, so we took a tapering bar, something like this. We took a tapering bar. So the pressure here it was 120 kPa, then the pressure here is 80 kPa. So that means by creating a pressure difference between these 2 points, but that is from 120 to 80, we created a pressure difference. So that pressure difference resulted in the change in the velocity. So now, and also if there is a difference of pressure, so you can connect it to a manometer like this and try to measure that. That's what you did in your laboratories. So by creating a pressure, by reducing or by creating a pressure difference between any 2 points, we try to measure the deflection of the mercury. So by measuring the deflection, we can relate to and try to finally go ahead and find out the discharge. So that's why this principle is used in our venturimeter, orifice meter. So that there the principle is that by there we try to reduce the cross section area, create a pressure difference between any 2 points, okay, and then we measure that mercury level and try to find out the discharge flowing through the venturi meter. So that is what is the principle which I'm going to tell you in the next few classes, where the applications of Bernoulli's equation will come. So here, by applying Bernoulli's equation, you are able to find out the discharge. How do you are able to find out the discharge? By knowing the pressures at any 2 points. So by knowing the pressures at any 2 points, I'm able to find out, okay, with loss, without loss, anything, but I'm able to find the velocities. From velocities, I'm able to find the discharge between the two sections. So this is the concept of this particular problem, which I wanted to tell. So now, here, this is one thing you should please remember, that this is the mistake, common mistake done. Specific weight is nothing but zero point 0.8 into 9.81. So this mistake is generally you neglect this, because oversight. This is not that you don't know. This is the oversight, because generally it is P by omega means 9.81. Okay, so G is anyway 9.81 because it is acceleration due to gravity. But here this term specific weight, whatever the liquid flowing, that specific weight you have to take. So please make a note of this, so when you solve the problems. And also please note the unit of this. This should be in 120 kPa or kilonewton. Then only this is 9.81. Suppose you take this in Newton per meter cube, then this has to be 9810. So this mistake also is generally done. So while you try to calculate suddenly the values and all, okay. So therefore both this should be the same units. So try to have same units as far as possible. So whenever you're solving like this, so KPI units if you have, then take 9.81. If you have only Newton per meter square units, then you should have 9810. Okay. So these things you should try to uh, see this problem. So your doubt will be cleared here. So because purposely I told that when the flow is taking place downward and when the flow is taking place upward, so what happens to the pressure at the lower end? So that is the problem where, so how the pressure changes now. So that the diameters of like it is given, which is zero point 0.5 meters and 1.5 meters. So two ends diameters are given, which is 16 meters long. So loss of head is 2.65 meters, which is given in either direction, whether you move from down to up or up to down, but the loss is given as 2.65 meters, which takes place. But the velocity at the smaller section, that is smaller section is at zero point 0.5 meters, which is given as 9 meter per second. Then smaller section is also given at the top. So then you have to find what is the if the smaller section is at the top, the pressure there is 2.15 meters of water. So pressure head is given. So if pressure head is given, so then it is P by omega. If only kPa is given, it is only pressure. If pressure head is given in terms of water, then directly P by omega it is. Okay, so be careful of this. So since water is flowing, it is already in meters of water, so no problem. So directly you can substitute a 2.15. So now I'll represent that by the sketch. So this is the sketch you have. See here. So what I told, smaller section is zero point 0.5 meters, larger section is 1.5 meters, which I have represented. Then if the smaller section is at the top, so I represented smaller section at the top. Then the pressure head here at the smaller section is 2.15. So you can name as it. You can name this as 1, this as 2. So now at the flow direction, I will represent this as 1. Okay, this is 1, and this as 2. But see this here. Your doubt is clear now. So now datum have considered down only, so that this will be a positive value. So since I named this as 1, you can name this as 1 and this as 2 also, no problem. Okay. So writing is very easy because I have seen this direction of flow and I have written this as 1 and this as 2. Okay. So because when the head loss is given, you should add to section, because the flow is taking place from this to this downward section. You have to second section you have to apply. So that's the reason I have taken this as section 1 and this as section 2. See now, so the problem is that everything is given. Okay. So now head loss is given 2.65. So when the flow is downwards, so velocity is given, velocity is given, which is the velocity at the smaller section is given. So that's why, since I named this as 1, so I wrote this as v1, which is 9 meter, and the pressure head is directly p1 by omega, which is 2.15. Knowing this velocity, I can calculate velocity here also, because a1 v1 equals a2 v2. So when I do this, a1 v1 equals a2 v2, I can find out v2. So v2 is 1 meter, because diameter is large, area is large, so velocity will decrease from 9 meters to 1 meter. It will decrease. Okay, so this continuity equation. Now you apply. See here. So when I, so this is very important. So when I apply, so when the flow is taking place from this section to this section, so I took this as first section, which I wrote it as. For the second section, when the flow is moving towards this side, the second section I've added the head loss. So this you have to take care. So that's all. This concept you should take care. Now you just substitute the values and get me the answer. So you have to find the pressure at the lower end. So P2 can be calculated. So P2 is 192.055 kPa. So this is the problem where when the flow is taking place downward and the flow is changing. See now, the sketch says concentrated. It is not the concern of section 1 and section 2. Anything you can do. So now I will retain this section 1 and section 2 as it is, and now the flow will take place upwards. So flow is, so these all will remain same, because the sketch I don't want to change. So when I see here, Vinay, that when the flow is taking place from section 2 to section 1, so what I will, how I will write this equation, I will write left hand side, because section 2 to section 1, then I will write here what I should write, P2 by omega plus V2 square by 2g plus Z2 equals P1 by omega plus V1 square by 2g plus Z1 plus head loss. Like this I have to write. So this is so so if you want, you can change the name for the next one thing and write the same equation. It is left to you, but the concept is like this. Okay, so whenever you try to write the direction of the flow for the second section, because when flow takes place from one section to another section, then only the loss will take place. So they would add to section 2 always. Section 2 means downward sections. Okay, no, it is not section 1 or section 2. It depends upon how the flow takes place. See here in this problem. So now uh, so what happened is, just for avoiding confusion, I have retained the same thing. So oh, sorry. Okay, have retained the same thing, section 1 and section 2, but only thing is the direction I've changed it. So therefore, they have said that velocity at the smaller section is 9 meter per second and pressure head is same. But I want to find out, this all V2 also will remain same, because area doesn't change. See here, see how I applied now. So see this you try to so because this is now flow is taking place from here to here, for down the next section I've added head loss. So that's why I've changed this. If you don't want to like this, always you want to write like previous equation, then you have to change the sections. You make this as 1 and this make as 2, and then write accordingly. So you unnecessary you will get confused. So whenever you write this as 1 and this as 2, then what you have to do, this you have to write it as V2 now here for this problem. For this you should write V2, which is 9 meters, smaller section, and smaller section is 2 now. So then P2 by omega you write. So this is, then you change this P1, V1, Z1 and P2, then add it. So accordingly you will get the same answer. Okay, so no confusion of the sections like this. So now when we, what is asked, the pressure at the larger end is asked. So therefore that is what is pressure at the larger end means, we have maintained as P2. Okay, so which is the pressure at the larger end. So this we want. Okay, so similarly the pressure at the smaller end is given, velocity is known, Z is known. So now see here, so if this is Z2, which is 0, and Z1, because we have taken section 1, so this is, so it is here you have to substitute 16 here. Okay, so be careful, that's all. So where this won't change, this won't change between the 2 points, only this the direction and the head loss only you have to write it correctly. So this the pressure you say now it has increased. Now from there it has become 250.9 kPa. So this is about your this one. Uh, ah, this problem is I solved one problem with a loss of head given as a numerical value like 3 meter 2.65 something like this, but this has given as a different something like 20% of difference of velocity heads. So then still we are able to calculate the discharge. So here the here what I have given is that it is 450 millimeters of mercury. So now you have studied a lot of pressure chapters and all things. You should be able to convert this into kPa. So hope you know how to convert into kPa. So how to write P1 now? Pressure at the lower end and pressure at the upper end. Suppose you want to convert this, so it is 0.45 meters. So how to convert into meters of water? How to convert into, because water no, so here, see, here it is oil. So let me what I should do, I'll first take pressure. How to convert into pressure? What I have to do? What I have to do? This, because it is H is P by omega. So if I want pressure, I should multiply by specific weight. So because it is mercury, so what I should do? It is 13.6. 13 point. So this is very important. 13.6 into 9 point. So this you always don't multiply by specific gravity and all those things. So always convert into pressure units. So this unit will be kilonewton per meter square. Then P by omega. Omega is oil. So zero point 0.8 into 9.2. So like this you follow. So otherwise unnecessary you will get confused. So if you multiply by only specific gravity, then it will become meters of water. Then you should divide by 0.8 to convert into meters of oil. So that all you will get confused. So if it is 450 millimeters of mercury, then you multiply by specific weight of mercury to convert into kilonewton per meter square. Then you apply in the equations. So, okay, so hope you know this. So that's why I took this problems to make you understand about how to convert into pressure units. So this I want it in pressure, and here this is already is in pressure, so no problem. So this is already in kilonewton per meter square. So the difference in elevation is also 4 meters given. So first you have to solve the problem neglecting losses. Next you have to solve the problem considering the losses. Okay. So this is the problem. The flow is taking upwards. So I have named this as section 1 and this as section 2. Okay, since the flow is taking upwards, I have named this as section 1 and section 2. The difference in elevation between the 2 points is 4 meters. So therefore, I have taken this datum. So Z1 is 0, Z2 is 4 meters. Now what is given? Diameter, having diameter 1 meter at the bottom and top 0.5 meters. Got it? So the pressure at the lower end is 1. So P1 is given, which is 0.45 into 13.6 into 9.81. So that gets converted into P1. Then pressure at the upper end is 20 kP. No need of conversion. It is directly 20 kilonewton per meter square. So now all the values are given. So what else is required? Velocity is okay. So we have to find the discharge. Okay, velocity, what you have to do is by continuity equation you can get a relationship between v1 and v2. So pi by 4 1 square into v1 is pi d square, that is pi into 0.5 square by 4 into v2. So we'll get relation between v1 and v2. So you can write v2 is equal to 4 times v1. Okay, you can solve this. Pi by 4 cancels. 1 by 0.5 is half into half is 4. So 4 times you will get. Okay, so that is 4 times v1 you will get. So this you take it and put it in the Bernoulli's equation. So since the flow is taking place from 1 to 2, so I have added head loss to this section 2. Please note, add loss to section 2. So this is what is I have added. So now you know the pressure at each of the points. So see here, I have converted in meters. Then this is specific weight. So I got kPa, but this specific weight should be very carefully taken because oil is flowing. So this is only to convert into pressure. After that, you should divide by 0.8 into 9.81. So that's what I have done. So 60 I have taken and divided by 0.8 into 9.81. So V1 square I kept it as it is. Z1 is 0. Then okay, sorry, this is P2. Okay, so this is P2 by omega. So similarly, V2 I have replaced as 4V1. I have replaced here and I have solved for V1. So when I get V1, so which is 1.19, I multiply by 4, I'll get V2. So Q is A1 V1 or A2 V2. Both will give the same answer. So 0.941. 0.941. So this is the discharge. So now so when this problem was taken only to say that how to convert this into pressure. So that's all. Otherwise it remains same as the previous problem. But now if I consider 20% loss, so here loss should be 20% of the difference in the velocity head. So sometimes they'll give 20% of velocity head at section 2. Then it is zero point 0.2 into V2 square by 2g. If sometimes they'll give 20% of velocity head at section 1, then it is zero point 0.2 into V1 square. If they give difference, then zero point 0.2 into v1 square by sorry, this is more, v2 is more, so it is v2 square by 2g minus v1 square by 2g, because v2 is always more than v1. So then you should write v2 square by 2g minus v1 square by 2g. So that's the difference of the velocity head. Okay, so that's how we solve this problem. So considering the losses, so now see here, zero point 0.2 v2 square by 2g minus v1 square by 2g. So what is V2? It is 4 times V1. So you can express this in terms of V1 square. Okay. So so don't take these values of V1 and V2 here. So this problem is over now. So this is the second problem. So by considering, we don't know the value of so now discharge changes because we have considered the losses here. There losses are not considered. So it comes in terms of V1 square. Now apply Bernoulli's equation. When you apply Bernoulli's equation, so wherever you know that same pressures will be there, so but only thing is instead of there, head loss will be considered, which in terms of v1 square. So here v1, here v1, here v1. So v1 gets solved. So when you apply, so it will be 1.16. Similarly, 4 times v1 will give 4.787. So knowing this, you can find out the discharge, 0.939. So last time you got 0.94. So 0.941. Now it is slightly changed, which is 0.939 meter cube per second. So this is about the considering the losses properly, correctly taking. Please note the pressures can be in terms of kPa, can be in terms of millimeters of mercury, so that you should know how to convert into kilonewton per meter square. So that's why that pressure chapter is very important for us. With that concept we are trying to relate here, so because nothing is waste here. So always whatever you studied should be put here in this values. Sometimes what happens is vacuum also will be given. Be careful. So that time you should attach a minus sign. So okay, so if they suppose they give as for 450 millimeters of mercury in brackets vacuum. So vacuum means it is minus. So you have to attach a minus sign to the pressure. That you know. So only that changes can be given to you. Okay. So I told you that this about this factor, which is we assumed in Bernoulli's equation that velocity is uniform across a section, but actually velocity is not uniform. So velocity will be zero at the boundary and will be maximum at the center line. So therefore, by taking as velocity as uniform, so we get velocity head quite less than the actual velocity head that is usually takes place in a pipe. So therefore, a factor is applied, which is known as a kinetic energy correction factor, which is alpha, which is generally more than 1. It has to be, not generally, it will be definitely more than 1. So 1.1, 1.2 factor will be applied just to make a correction, because we applied uniform flow. So that's actual flow is parabolic distribution of velocity distribution. So in order to account for that, so we say that we take a factor which is called alpha. So here that is what is the kinetic energy per unit, that is v square by 2g, v1 square by 2g or v2 square by 2g is got based on the assumption that velocity is uniform, but actually it is not so. Because in real fluids velocity distributions generally is not uniform. So there, that's the reason velocity will be different at different sections, at different points along the vertical section. So generally the total kinetic energy will be has to be, because if you write an expression for kinetic energy and integrate it, you will get the total kinetic energy. So that is what it is meant. So now how to write that? So no, derivation is not required, but anyway I'll tell that. So mass, if you want to write mass per unit time, so mass by time, mass is nothing but density into volume. Density into volume per second is discharge. So discharge is velocity into area. So therefore, if you take an elementary area, so you can calculate mass per unit time, which is density into this rho into q, rho into q. So q is velocity into the area. Similarly, if you want to calculate kinetic energy, it is half mv square. So take half m, this is m into v square. So that is v, so half into mass into this. So now you, if you want total kinetic energy, you integrate this. So when you integrate this, so that is integration is this. So this density is written as omega by g. This half comes out. So it is integration of v square into v. So it is integration of v cube, integration over the entire area. So like this. So now, so this is one equation. If you assume that kinetic energy is totally differing from section to section, or across a section, but in our derivation we took it as velocity v, capital V. So we took it as a mean velocity. So since we took the mean velocity, actual kinetic energy which is obtained by that integration is quite more than what we took it from our velocity v. So that's why a kinetic energy correction factor is applied. So therefore, when you try to apply the same equation, see here, so this equation, so when you take capital V, so here, so you have to take omega by 2g into v cube. Okay, v cube like that. So then multiply by, so v cube we took, area we took, instead of dA we took area. These all terms remain same, but we applied correction factor. So this is the kinetic energy which will match with the kinetic energy that we had with our taking the elements. So you try to equate these two. So then when you try to equate, you get a factor called the kinetic energy. So this is how we do it in like, if you know the expressions for V, so we try to integrate that and find out the kinetic energy. So now I'm not interested in this particular, suppose, okay, you note down this particular equation which might be helpful for you. So suppose for a particular cross section area, for a particular section given, cross section area is given to you, so you can substitute here. Uniform velocity might be given to you, average velocity over the section is given to you, and then they will give an expression for velocity. They will give an expression for velocity. So you try to integrate that over the area, so that that expression. So then substitute here, then you will get the correction factor, that is alpha. Okay, so this is how you try to do this. So I'll try to include one or two problems. So one problem in the maybe later on when I do the problems on this. Okay, why I wanted to tell is that, so now alpha depends upon the velocity distribution here. So generally for the turbulent flow, which is quite near to your this uniform flow, so therefore the factor somewhere it is nearer to 1. So therefore 1.03. So please note that turbulent flow generally alpha is what 1.03 to 1.06. But when you come to here the laminar flow, so generally the value of alpha will be equal to 2. So therefore you take it as alpha is equal to 2 for laminar flows, and for turbulent flow you take it about 1.03 to 1.06. So these ranges will be asked for you, so that you should be able to tick that. So kinetic energy factor for laminar flows is around 2. So that's it. So now the same Bernoulli's equation will be modified. So please note this expression. So wherever kinetic head comes, there the factor should be applied. So alpha 1, alpha 2, like this. So generally they will not give like kinetic energy factor for section 2 one different, and so they will give one kinetic energy. So that is same as 1.52, like this. So you multiply, don't forget to multiply by, if kinetic energy factor is given in all the problems that we did, so don't forget to multiply by this factor. So if it is given, if it is not given, assume it to be alpha is equal to 1. So therefore in your even in NPTEL also, when you took fluid mechanics, there this factor was some, there was one or not two problems where this kinetic energy factor was also given. So therefore if you miss this and try to calculate this, then you might go wrong also. Okay, so that's the reason why the kinetic energy factor has to be accounted, just to account for non-uniform distribution of velocity. If there was uniform velocity distribution, then it would not have been, alpha would have been 1, then it would have been v square by 2g only. So this is what I wanted to tell you. So please make a note of this, which might help you in some of the problems where you are trying to solve if alpha is given. So all other problems will remain same except for